In section 6, we're going to be looking at area, volume, and average value. And honestly, most of my focus here is going to be on area. I want to show you how it works for volume, but we're not going to execute that as much in this course. We do cover it quite a bit in Cal 2 if you are taking a calculus sequence. But for the sake of business calculus, I want to show you how it works, but we're not going to practice with them or even take an exam over them, but we are going to with area and see how that works. We have already used integrals to find the area between the graph of a function and the horizontal axis, but integrals can also be used to find the area between two given graphs. And so if we have f of x being bigger than g of x, some function that's larger than the second one for all x in our short interval of a to b, then we can approximate the area between f and g by just partitioning it off into intervals, somewhat of what we were looking at with our Riemann sums when we were getting that idea in section 1 of those definite integrals. And so the height of each of those rectangles would be the height of your top function minus the bottom function because it's been moved up or down off that x-axis. So if that's how we're figuring out the height using maybe our rectangle method that we looked at, then we are actually just looking at the integral here, or the area between two curves of f of x happens when we set up our definite integral with f of x being our top function minus g of x, our bottom function. And it says make a graph to be sure which curve is which, and I'm going to show you how to execute that. When we're working with our homework problems, our exam problems, you're either going to be given the graph and you have to look and go, okay, which one's on top or bottom by what they're labeled, or using your knowledge of your parent functions, you can hand graph it and then figure out from there. I'm not going to throw you any kind of curveballs of, oh, here's this crazy function and you need to be able to graph that without a graphing calculator. So I am aware of the graphing techniques that we are able of, and I'm going to expose you to some different things in the homework and the lecture here. But at the end of the day, the things that we're going to practice, we're going to do based off what we know from a given picture or from being able to graph our parent functions. And I want to show you that here today. And so let's just kind of start out with an example here. In this example, it has two objects that start from the same location and travel along the same path with velocities, and it gives us those two functions, meters per second. How far ahead is A after 3 seconds? And so this is showing us that for this problem, we need to find the area underneath that curve, and let's see how we're going to set up that integral to execute that. So we're going to be doing a definite integral, and we're going to be doing it from 0 to 3. 0 is where these curves are touching here, and we said after 3 seconds, and so that's how we get this area in between. Again, this is an example of one that it's going to give you a graph. See, it has it labeled, and you're going to do your top function, so t plus 3, minus your bottom function, t squared minus 4t plus 3 dt. So in setting up your definite interval, you're doing your top minus your bottom. I would go ahead and do your algebra and clean that up. With this problem, I would go ahead and distribute those negatives out and then combine like terms. So you can see we have a negative t squared. I have a positive 4t because I distributed that negative, and a positive 1t, so that gives me plus 5t. And then negative 3 and positive 3 would cancel each other. So this would be the actual function that I want to integrate. And so integrating that, I would add 1 to the exponent, divide by the new exponent, add 1 to the exponent, divide by the new exponent, and we're going to be integrating from 0 to 3. So we're going to have to use our calculator to help us with that. That would be the negative of 3 cubed over 3 plus 5 times 3 squared over 2. I'm going to take that value and subtract off negative 0 cubed over 3 plus 5 times 0 squared over 2. Those just give me 0, so we're just looking at this value here, and that gives me 13.5. I would definitely use the on-screen calculator when you're working through these. It's going to help you to kind of see the whole function you've created and get your parentheses the way you need them. So finding the area between two curves is not a different evaluation in any sense. We know how to do definite integrals. We know how to integrate these functions. It's just this one little added step of doing top minus bottom to help you with that. And so be careful with your setup. Be very detail oriented, because the detail oriented is going to help you to not lose a small little piece somewhere, and then show all your steps in between. Use your on-screen calculator underneath your homework problem to assist you with that. Now I'm going to do more problems with area when we get towards the end of the lecture, but at this point I would just set your pen down, and I want to kind of discuss some things with you and show you how things work out, but I am not going to quiz you, have you practice, or work through volume problems in those situations, because we're just going to look at the business calculus part. But I do want to expose you to this and the capabilities of what you could do with it. In the next part for volume, we're just going to talk through it. I'm not even going to work out some of these problems. I just want to show you the ideas of it. So how volume works is basically you start with the area like we just created, or we've been finding the whole way, and the region below a function on the interval from A to B. So we're going to take that region and you rotate it, pretty interesting, rotate it around the x-axis, and you can see from this 3D model, it creates our solid shape. And so the only added fact in order to find volume that you would have to do is that rotation, which is just think a bunch of circles, and so you see pi added in. And so again, I'm going to kind of gloss over this because we're not going to execute this in this course, but I want to show you kind of the end game of what you could do with areas. So if you take all these areas we have been creating with our rectangles and you begin to rotate them, you think about, oh, well, this is a bunch of circles that are being cut out of our 3D shape here. And so the area of a circle is pi r squared, where your r is the height of your rectangle, and then multiply that by the width of it. And so you get functions that will look like this, pi times your function being squared. And so then you integrate that, you apply your definite integral from B to A, and you get the volume of some curve being rotated around the x-axis. Now, of course, we can amp that up and we can move that rotation around. We can cut a hole out of it and make some kind of donut. And the book goes through some examples, but I want to kind of expose you to that, and especially pretty neat, this picture here to start with, on how we can take this concept that we've been working with area, do a slight rotation, which puts in just the fact of, let's look at that formula there, just puts in this pi and squaring our function. And so those two simple arithmetics, really, because we know how to square and multiply by pi, gives you a volume of a solid. And so pretty neat there that the volume of a solid can be obtained just by rotating around that x-axis. But again, I'll save that conversation for another day. If you change majors or change sorts and you end up having to go into that calculus sequence, we do a whole chapter over volumes and rotations, etc. But what I want to go ahead and jump into is moving down here into an average value of a function. And so this will be our next concept for this section. But again, just wanted to expose you to volume. Average value. So nice little yellow box here. It says the average value of a function on the interval from A to B is given by, and as you can imagine, taking the average of something is just dividing by how many that you have. And so for this, the only added thing that we are putting in here now is this 1 over B minus A. We are putting this in the front of it so that it is a coefficient because it is a defined value. And then we'll just integrate like we're used to doing. And so look at this example here. It says, during a 9-hour work day, the production rate at time t hours after the start of the shift was given by the function of cars per hour. Find the average hourly production rate. And so this keyword right here of average hourly production rate cues us that we're going to have to use this form here. And so I'm going to say, okay, well then we are integrating, and our function we are integrating is 5 plus the square root of t dt. We are integrating it, it says, during a 9-hour work day. So I'm going from 0 to 9. The values that you have here of B and A are the ones that you're going to be averaging. So 1 over 9 minus 0. And then we have our dt. And so the setup is very similar to what we've already done, but we're now just putting that 1 over 9 out front. So I have a 1/9, the integral from 0 to 9 of 5 plus the square root of t dt, Integrating that, I'm going to go ahead and change that radical to a 1/2. And so then I can integrate that. That gives me, just moving up here, 5t plus add 1 to the exponent, which would give me t to the 3/2. And then dividing by 3/2 is multiplying by 2/3. And I'm going to integrate that from 0 to 9. And I have this whole function times 1/9. And so I'm going to go ahead and distribute that to give me 5/9t plus 2/27t to the 3/2. Integrate it from 9 to 0. Now plugging in zeros is just going to give me zeros, so I just need to plug in a 9. So I have 9 plus 2/27, 9 to the 3/2. Again, use your on-screen calculator, and that gives me 7 cars per hour. And so you can see the only thing that we have changed was this 1/9 being played into here. The rest of the evaluation and processes were from previous sections that we've already been working with. So in general, the average value of a function will have the same units as your integrand because you're only changing that little 1 minus, putting that 1/b minus a in front of what you have been doing. So my next thing I would say is why? Why do we even want to look at the average value of a function over an integrand like this? Well, function averages involving means and more complicated average are used to smooth out data so that the underlying patterns are more obvious and to remove high frequency noise from certain signals. And so in these situations, the original function is being replaced by some average of that function. So if f is rather jagged time data, then the, say, 10-year average of f would be a better idea of what's going on over that curve. And so let me show you this function. You'll notice on this graph, this is the surface temperature record from 1980 to 2005. And so it has 2 different pieces of data in there, and we can see that the black line is our monthly average. Where they put the dots was our annual average, and then they took the red line and made your 5-year average, and it was over temperatures because, well, if you have been in Texas very long, you know, one day it's been a crazy year. In 2021, we had snow at 0 degrees for quite a few days. But then a couple weeks later, you're at 80 degrees. And so you can imagine if you're looking at the temperature in Texas, in East Texas, where Panola College is, that the temperatures would be jagged all over the place. You can start the morning off at 32 degrees and by afternoon you're at 85. And so the jaggedness of it, an average would help better to smooth out that curve and see what's going on. And then if you even average that over monthly, annually, or even 5 years, you can see better curves. And so that's why your average is going to come into play. And especially if you have they call it very noisy data, or jagged data to go with it. So let's practice some of that information that we've been talking about. Let's look at some areas of curves, and then let's also kind of look at some other, maybe possibly some averages, just to see what you're going to face as you go into and attempt some of these homeworks. And so here's an example. It says find the area between the graphs of f and g for x in the given interval. And so again, this goes back to that first example we did, and we only did one of them. So here's our extras. We're going to be setting up a definite integral. It's going to go from -1 to 2, and it's based off this interval they gave us. Then we need to figure out, is x squared plus 3 or is 1 our top functions? And so I told you, if you're faced with functions and not given a picture, you're going to use your knowledge of your parent functions to figure this out. So x squared plus 3 is just a quadratic that has been moved up 3. It looks something like this. And then g of x equal to 1, that is a horizontal line at 1. And so then if I go from -1 to +2, I am looking for this area here. So you can see my quadratic would be the function that's on top, and so that's going to be the function that goes first, x squared plus 3. minus your bottom function, which is just 1. And we're doing it in relation to x. So first clean up your integral before you start integrating. And so positive 3 and negative 1, that gives me x squared plus 2 dx. Then I'm ready to add 1 to the exponent, divide by the new exponent, plus 2x, integrate it from negative 1 to 2, and then you're into your evaluation. Use your calculator to help you with this. So it gives me 2/3 over 3 plus 2 times 2 minus, be careful because a lot of times we use 0 and that second number phases out on us, but this one will not. Negative 1 cubed over 3 plus 2 times negative 1. So that gives me, let's see, 8 over 3 plus 4. I'm going to go ahead and distribute this negative throughout so I don't lose it. Negative 1 cubed is negative 1 over negative 3 to give me a positive 1/3. Negative 2 times negative 1 gives me a positive 2. Then I can put this together to give me 6 plus, putting those together, 9 over 3. And 9 over 3 is just 3. So this gives me a value of 9 for the area between those two curves. And so you can see my knowledge of parent functions and simple transformations that you learned in previous courses, along with our definite integral, helped us to see this. But again, the key is going to be your setup. Can you get this setup of your top function minus your bottom function, and then we're back into definite integrals. Let's do another one. Now I picked another one again. I've got 2 more that we can graph and kind of see what's going on. And so the first thing I'm going to do is I'm going to kind of graph this out to the side. So if f of x is equal to x squared, that's just a parabola centered at your origin. And then g of x is equal to x, and that is a straight line going through your origin. And because we're only between 0 and 2, let me erase this and let's zoom in on that first quadrant and be a little bit more accurate. So let me make some tick marks here. With this function, your parabola is at 0, 0. If you plug in 1, that would be 1, 1. If you plug in 2, that would be 2, 1, 2, 3, 4. And here is your parabola. And I'm just looking at that first quadrant because of this interval. And then if g of x is equal to x, that means it's going to be at 0, 0, 1, 1, 2, 2, 3, 3. And so what's happening is you're here. So what's interesting is we're going to have to take this in 2 parts. We are going to have to first look at this situation that's going on right here. And then we're going to have to look at the situation to the right, because to find this area, I want that area in between there. And then, because we're going all the way over here to 2, I'm going to have to find this area in here. If you zoom in even more on your function and just look at what's happening, we know that there's a straight line here. But what's happening with your curve is it's going to loop up into that. And so really, the in-between is going to have your g of x on top. And so we're going to have to break this up and look at 2 different areas. First, between 0 and 1, and that's where our straight line is on top minus our quadratic, plus between 1 and 2, where our quadratic is now on top, so x squared minus x dx. So just because we're looking at top and bottom doesn't always mean we do f minus g. It might mean at some point we need to switch over because of where they're crossing and the area in between the 2 curves. Then I'm going to integrate. So that gives me x squared over 2 minus x cubed over 3. I'm going to integrate that from 0 to 1. Plus, it is a similar function, so that would be x cubed over 3 minus x squared over 2. And I'm going to integrate that from 1 to 2. And so very similar, just kind of changing of signs. If you plug 1 into your front one, you get 1/2 minus 1/3. Plugging in 0 gives me 0 value. Plus, in this back one, I'm going to plug in 2, so it gives me 8 over 3 minus 4 over 2 minus, because remember, you do the 2 minus the 1 valued, so it would be 1/3 minus 1/2. And then to finish this out, I'm just going to put all those values together. I'm going to go ahead and distribute this negative so that I can just combine like terms. And so I have, let's see, 1/2 plus another half and that gives me 1, minus 2, so that gives me a negative 1, plus negative 1/3, and 8/3 gives me 7/3, minus another third gives me 6/3, which is 2, and then negative 1 plus 2 is just 1. And so the area of this little sliver here and then this top piece here gives me a value of 1 unit. So I want to do this one specifically because I want to emphasize your parent function and how we might need to zone in on a couple areas in order to figure out where is it really on top, where is it really on bottom, and maybe you might have to separate that out and do it in pieces. Let's do one more with this parent functions and graphing, and I'll do this setup. We may not work this one all the way out. So let's see, 4 minus x squared. So that means we're going to be shifted up 4, 1, 2, 3, 4. And then that negative is going to flip my U shape downward. Then g of x is equal to x plus 2. So I'm going to go up 2, and then my slope will be up 1 over 1. And so this would be my line. Now we want to integrate this from 0 to 2. And so more specifically, let me find this value here, my x-intercept, because this was just a rough drawing. I do want the area between the two curves. I want to make sure that where does 2 lie in this. And so if I plug in 2 to my x squared here, 4 minus 2 squared would just be 0. And so this is the value of 2. And so if I want the area between the curves, I'm going to have to do 2 parts again. So right here, we're switching. And so the blue part is on top and the red is on bottom. And then over here, the red part is on top and the blue part is on bottom. So I'm going to have to split it again. And so I need to find that split of where they are equal. So I'm going to do simple math over here. 4 minus x squared set it equal to x plus 2. And we're going to solve that out to figure out where this crosses. Now it crosses down here as well. This is a quadratic, so we're going to get 2 answers, but we're going to take the positive one. So I'm going to move all these pieces to the right, and so it gives me 0 equal to x squared becomes positive plus x, subtract this 4 over, and that gives me negative 2. If I factor this out, this gives me x and x. The sign is a negative, and so they're going to be different signs. And then what will multiply to give me 2 and add to give me positive 1, that's a positive 2 and 1. Solving that out, that gives me x plus 2 equal to 0, so x is negative 2. X minus 1 is 0, so x is 1. So negative 2 would be where they cross down here. Positive 1 is where they cross here. So I'm going to set up my integral, and I'm going to go from 0 to 1. My quadratic is on top, 4 minus x squared, minus my linear function, x plus 2. I want to make sure I put that in parentheses so I don't mess up a sign. Plus, I'm going to integrate from 1 to 2. Now, my red function or linear function is on top, so x plus 2, minus 4 minus x squared. Again, use parentheses so you don't mess up your signs. Let's clean this up. So distribute that negative. I get the integral from 0 to 1 of negative x squared minus x, 4 and negative 2 gives me plus 2, plus the integral of 2 to 1, distribute this negative, that's going to give me a positive x squared plus x, 2 minus 4 is negative 2, and I'm going to integrate dx. Then we can do our integral, evaluate, add together. Just be careful with your details. But again, I want to do this one because I want to show you how we can graph and figure out how which functions on top and bottom. We can find the intersection of where we need it to cut this in half. And then from there, I feel like you can apply your definite integral. But if you need more assistance or more explanation, just please reach out. And so these area between two curve, it's going to be your details in algebra that get you, not necessarily if you can do integrals and definite integrals. Let's go ahead and do a couple more examples of average value. And so I've got some here. It says find the average value of f over the given interval. And so again, the only thing we're doing with average value is we're going to do 1 over b minus a with our definite integrals that we have already been setting up. And so I'm going to say, okay, I'm integrating from 0 to 2, so that's 1 over 2 minus 0 of our function x squared dx. And so I'll say 1/2 the integral from, let's go ahead and integrate it. So it would be add 1 to the exponent, divide by the new exponent. We're integrating from 0 to 2. Let's go ahead and combine that together to give me x cubed over 6 from 0 to 2. And then we'll just plug in 2 cubed over 6 minus 0 cubed over 6, which is just 0. So it gives me 8 over 6, reducing to 4/3. And just leave that as 4/3. Don't go in there and start changing that up and do 1.3 repeating. We do like exact answers when we're working through this. So I hope that helped you with your average value as well. Again, it's just adding in that coefficient. This is a little bit harder than just your basic integrals or definite integrals, because in those previous ones, you got to set them up. You got to consider the picture. But again, in terms of homework or exams, you're either going to be working with parent function transformations that you can easily graph and look at, or you'll be given a picture to assist you and help you with that problem. If you have any more additional questions in regards to this section, please just reach out.